again, a reminder that this is not stuff that's on the midterm. But this will be basically all of exercise 7. So we're going to talk about lifetimes, populations, ages should really be in there as well as lifetimes, and then start talking about stellar evolution, which is a pretty hard question because aside from some physics, stars sit there and they just twinkle Gesundheit for thousands of years over the course of human history, and we haven't seen them change, with a few exceptions. So how do we actually get meaningful observational information about stars and their life? And again, Friday we'll finish up whatever we don't talk about today. There's midterm, and then the week after that, next week, we'll just get really into all the interesting stuff. So star birth, which we'll start talking about today, and star death, and then exoplanets, black holes, general relativity, supernova. So this is basically like as of, past the midterm is when we go all sci-fi. So really quickly, and you could consider this midterm review too, we'll review what we talked about with main sequence stars, which is to say what it means to have and how to read an HR diagram for the main sequence strip, which is the hydrogen burners. And then we'll start talking about the thing that we left out of the picture when we came up with our somewhat flawed, as it turns out, nebula theory of planet formation. And then how do we turn the lifetimes and ages of stars? Remember, they're two wildly different things. And some ridiculous cartoon to reinforce that fact. So this is what we know on a star-by-star basis and via assumption. So based on our own observations of our own sun, honestly, there's really only one other thing in the universe, one other force of physics that we know about that could be powering the sun with that power, and it's gravitational contraction, and it wouldn't last long enough. So we know that our sun is powered by fusion of hydrogen into helium in the core, so like middle, 15% or so. We can observe the temperatures of other stars through their color, so blue star, hot star, red star, orange red star, kind of cool, a little bit cooler than our sun, and then this red star, very cold comparatively at the surface temperature, the photosphere. And then if you have a really good spectrometer, which is to say take the light from the single star, break it up with a prism, look at all of it, now we can start talking about what elements exist within the star itself. And I'll say this is, you're not going to see this from too many stars because this is our sun. It's really close. We have a lot of light from it. So this is a beautiful spectra, but you can see every single line laid bare. And we're definitely a star that has a lot of stuff kind of sprinkled in the atmosphere. There's iron and cadmium and calcium and sodium and stuff like that, as well as quite obviously helium and hydrogen. So that's star-by-star basis. And then we started getting into trends. So we can do that to every single star and learn about their composition and their temperature. But now the other physics questions, like for instance, what their distances are, what their masses are, what their luminosities are, which is to say the actual physics of how much power they're putting out, and whether or not they're correlated. So the first thing we did was we took what you see from Earth, which is the apparent brightness of stars. So all of the stars in Orion, at least to the eye's precision, are more or less the same brightness, at least like the major stars. But once you can figure out distance, and it turns out that, for instance, Orion's left knee is almost a third as far away as that middle star in Orion's belt. So now you can start talking about, now I can figure out how much power it's actually putting out. So you have apparent brightness, how bright it appears, and the distance. You can figure out the luminosity, which is the actual wattage that the star puts out. And we measure them in terms of solar luminosities. So which one would be the brightest, roughly speaking, if they're all putting out the same amount of, they all appear the same brightness from Earth-ish? Yeah, so if they all seem to be the same brightness, the one that's the farthest would actually be putting out the most power. So appears dimmer and dimmer as you get farther away, but it's still just as bright as this guy. So it's got to be putting out lots of power. And we can do this. It was like a pretty big issue back in 1600 AD, but now we have space telescopes with binocular vision, and we can totally bomb the parallax distance problem. So we figured out mass the exact same way that you guys did in exercise 5. And you could do that. Like I could tell you, you could really just take this data with a period and distance and you could literally just plug in those numbers in the exercise 5 formula, and you could figure out the mass of that star. So it would come out in Earth masses, so maybe you want the sum number to be a little bit different, but that's not a problem. So, and we're really, this will turn out to be important many times later, is that we have a bit of a gift in the sense that 50% of stars-ish occur in binary systems. So there are lots and lots of visual or eclipsing binaries, so you can see stars pulling other stars around through the force of gravity. If stars didn't interact with other stars, this would be really tough, but we've got this. So we have mass. The thermal physics tells you some stuff about the radius, where there's a Stefan Boltzmann law that says if you're at some temperature, you can tell me how much power per area I'm putting out. So this is basically, think about putting the poker in a fire, and as the poker gets hotter and hotter and hotter, not only does it go from red hot to white hot, but it also emits more total power. So that goes like surface area, which in the case of a star is 4 pi r squared, times temperature to the 4th power. So we can figure out the radius of stars by going backwards. So we know the power they're putting out. We look at their color to get their temperature, and now we can figure out their size. And again, this is disturbingly not to scale in the brightness sense, because this star, this M star, should have maybe 1/10 of 1/billionth of the luminosity of this O star. But the sizes are to scale, so you can never get everything. And then finally, we had kind of a crummy estimate, but it turns out to be not so bad. And I'll just basically say the idea is right. It's checked down to here with observation, and beyond that, you're relying a little bit on nuclear physics calculations. But one of the few positive side products of the Cold War is that we know a lot about nuclear physics fusion calculations, because we were wondering, how we could kill the world over 50 times instead of 48. So it's pretty well checked out. The idea behind the lifetime is that a star, because it's powered by fusion, we're talking about main sequence stars, so specifically fusion from hydrogen into helium, they're powered by mass, so they're converting mass into energy. So you think about the mass of the star as like the size of its gas tank. And then you're thinking about the luminosity, the power output, as basically how many miles per gallon it's expending. So high luminosity star is expending tons of energy. It'll burn through its fuel faster than a low luminosity star, given the same amount of fuel. So it's really, you divide your mileage by the size of your gas tank, and you get a sense of how far you'll drive. Likewise for a star, if you divide the mass by the luminosity, you'll figure out how long it'll live. And these give you pretty good numbers, actually. So not too wildly off from the, like the official theoretical physics sanction number. And what we're going to talk about now is how you would observe this, how you'd actually get observational data on how long a star lives. Because, you sit there looking at the sun, waiting for it to burn out, you're going to be waiting for a long time. So the last thing to mention about that, again, is that the O stars are basically like the rock stars of the universe. They live very fast, 10 million years, sometimes less for the really big ones. And then the M stars, 10 to the 11th years, that's 100 trillion. The universe is only it's 100 billion. The universe itself is only 13 billion years old, so this is conjecture. There's no M star around that's burnt out and died of natural causes. So this is theoretically how long they would live if we can figure out how to make the universe live that long. But that's the really, philosophically right, but really quick answer. So any questions about that? Lightning review of what we did on Friday. Okay. So at the end of that, we constructed this. There are going to be other branches. There will be radii on this if you need radii. But this is the main sequence of the so-called HR diagram, so the Hertzsprung-Russell diagram. And if you think about it, it's kind of a 6 or 7 dimensional graph. So it has spectral type, it's got temperature, it's got color, it's got mass, it's got lifetime, it's got luminosity, and then radius too, if there's a radius on this. And if you tell me one of them, I can tell you all of the others. It's nice. So very, very highly correlated. Okay. So there's an aside that for some odd reason I think is appropriate to talk about here. I have no other way, there's no more reasonable place to talk about it, I think. It's like the same logic that underlies the gas tank calculation is that you can infer a little bit about the interiors of stars through these ideas. And remember that a star is a balance in between two types of forces. So there's the in-crushing force of gravity. So our star has 2 times 10 to the 30th kilograms of stuff, so aka a lot. So that's what's trying to crush the star. And then the pressure of the constant thermonuclear explosion in the core is trying to puff the star out. And fortunately, they're balanced, and fortunately, they're stable, where if one starts winning, the other one will compensate to take care of it. So that's really nice. And just through the luminosities and masses, you can actually deduce a little bit about what's going on in the interior of stars. So who do you think has the fluffier core, an O star or an M star, and why? So the way I would think about it is kind of the way that you think about the lifetime calculation. Is what does gravity depend on? What does pressure depend on? Less dense. So for instance, the core of our star, our G star, would be about 10 times the density of lead. I don't know if that means anything, but that, So if I have a handful of it, how much does it weigh? So I have a handful of an M star's core, a handful of a G star's core, and a handful of an O star's core. All the same volume. Which one weighs the most? And why? So how many people think they're all the same? Doesn't matter. People think the O stars have the fluffy cores. And people think that M stars have the fluffy cores. Totally even split. Somebody who believes that O stars have fluffy cores, what was your reasoning?
More pressure, a larger radius.
So the operative words in there, which with a little bit of distilling, that is a perfect answer, is the mass is the thing that's trying to crush it, right? So gravity depends on mass. And then what's the thing trying to puff it out? The radiation pressure. And that depends on the luminosity. So when I go from Sun to O star, you're absolutely right. So the radiation pressure goes up quite a lot. But then what happens to the mass? So I go from Sun to O star, mass increases by a factor of 30 or so. When I go from Sun to O star, what happens to the luminosity? Increases by a factor of 500,000. So again, the luminosity wins. And the luminosity, which is sort of the radiation pressure, which is trying to puff the star's core out, actually, fluffs it up and beats gravity. So in fact, O stars have fluffy cores, and M stars have very, very dense cores. And this would be just like a total bit of astronomical minutia if it weren't for the fact that stars in the middle that are a little bit more massive than our sun, especially towards the end of their lives, they don't really know if they're puffy cored stars or dense cored stars, and there's a sharp divide in between them. And what they start doing is they start pulsating. So they'll actually start beating very regularly. This is the total amount of, actually apparent brightness is the brightness that you would see. And it's wonderful because this is on a human accessible timescale. So for a variable star like this one in this cartoon that doesn't exist actually in nature, basically every 50 days or so, the star goes from bright to dim to bright to dim. In fact, Polaris, the North Star, is a variable star, and if you were to sit there painstakingly measuring its brightness over the course of a year, you would actually see that it varies back and forth. Turns out this is really important later on in the course, because these variable stars, there's a relationship in between their brightness and their period. But I'll just point that out now, because you can argue the answer based on the same sort of reasoning as we figured out the overall the overall lifetimes of stars. Okay. So remember that for 2 weeks. I'll remind you, don't worry. Okay. So now we're on this problem, and this is a pretty serious problem that it's possible we would never make headway on. I show you a collection of stars. This is probably out towards somewhere in the galactic plane. And they're all very pretty, and there's so much we know about them now, their temperatures, and if we had a spectroscope, we could determine a bit about their composition and their lifetimes. But now I want to know how old they are. So I would like to be able to point to a star, and maybe I'm trying to trace like the whole evolution of the galaxy or something like that. I want to look at this and say, how old is this star? Well, it's very blue, so I know it's probably less than 10 million years old. But in any science but astronomy, pinning some things' age down to within 10 million years would be a complete failure. So what about that? Geez, I can only pin that down to maybe, 10 billion years. So how do we find ages? Any possible ideas? Maybe not certainly not by looking at the star individually. I mean, there are some clues. So they pulsate differently as they get older or something. But you definitely don't look at this collection of light and read the age off of it. Stars do not develop wrinkles. They do not show any other signs of aging. There's no surface feature that you're looking at. It's just like it's saturated these pixels. You're not really, again, looking at the disk of the star itself. So it's just some light with some spectral lines etched in it. So how on earth are you ever going to determine the age? And before we go on, just a reminder, age and lifetime are not the same thing. This slide is here because every single midterm and every single quiz on stellar lifetimes and every single exercise 7, people confuse age and lifetime. Sea turtles live for up to 75 years. How old is this sea turtle?
Pretty old.
I don't know. Right? So the point is, I don't know. Yeah, less than 75 years. Unless you know something about sea turtles, you're in absolutely no position to make this statement. So this is like the issue we're in, but it's harder because, I could like pick this thing up and, cut it in half maybe, figure out something that way. It's old enough to have eaten lunch. Stars, no hope of doing anything like that. So just remember, age and lifetime are two different things, wildly different. Okay. This is going to be our trick. What we can't do is pretend that you know nothing about human biology at all. So you have no clues from gray hair and mode of dress, and there's sort of a meta clue in the fact that this is a black and white photo and a color photo, and that'll be our look back time thing that we'll get to in cosmology. But knowing nothing else, if I were to just give you these pictures of groups of people, so this is like a group of people in their high school reunion, and I won't tell you which one's which, what clue with the least amount of information could you possibly have that one of these groups is older than the other group without referencing anything about human beings?
There's less.
Less of them. Yeah. Great. So who's not in this group of people? Yeah. And in fact, the people with, like congenital heart defects and predispositions to cancer and stuff like that. And this is actually how we're going to roll. So this has an analog in space where these people who grew up in the same town and, some of them moved away, but some of them stayed, they actually were born together. They're a cohort. They live together. Like for stars, they'll be gravitationally bound. And the older they are, the fewer of them we'll see. And in fact, we know which ones are going to go first because we know stuff about lifetimes. So this is kind of it. We'll basically look for groups of stars that never left their home. And to understand why you can do that, we need to go back and talk a little bit about solar system revisited and talk about the thing that we actually didn't talk about, which is the star, the part at the center. So this is nebula theory. We did this when we came up with a somewhat fairy tale, just so story about how our solar system was formed. And it was basically, in the beginning, there was a cold cloud of gas. It was like maybe a light year and a half across. It was sprinkled with a little bit of heavier elements, a little bit of metal, a little bit of volatiles, mostly hydrogen and helium. And then something bumped it. And then gravity started taking over, and gravity shrunk it by a tremendous amount into maybe 100, 200 astronomical units. As it shrunk, it did the figure skater thing and conserved momentum and spun out into a disk. And then out of those disks, planets formed, and then voila, we had a solar system. So that was the broad story. And getting more detail about that took a long time because cold, chemically enriched clouds are actually like the bane of all astronomers because they absorb visible light. So this is actually the ideal place to look for a new forming star, right? Inside this dark, inky black cloud of gas. So we kind of forgive people for getting some details wrong in nebula theory because it's literally like one of the worst places. It's up there with like inside of a black hole as far as observational astronomy goes. So somewhere inside of this, all the details of star formation are happening, and we just can't see it. This is another picture that's just completely ridiculous. This is, I think, the ink blob nebula or something like that. So cold cloud gas, and probably there's star formation going on. So this requires one of the things that really, really required, and only great progress has only been made recently, is you need non-visible or infrared light to do this. So this is the exact same nebula, but now we're looking with an infrared telescope instead of instead of visible. So you can see something. And I just like this because, one, this whole documentary is actually really good. And secondly, whatever this is, don't buy it. What's that? So dust is evil because dust is more this than this. So, and what dust means is not the sort of stuff that you find in the corners of your home. For an astronomer, what dust is like these 1-micron grains of, atomic things that have slowly aggregated. And so what it does is it doesn't scatter beautiful individual lines that says, aha, dust, I know what you're up to, and what you're made out of. Dust actually does more like black body scattering and tends to just eat entire regions of the light coming through it. So typically, like cosmic dust just eats visible light. And because of its size, it actually leaves infrared light alone, usually, typically. So the cloud is usually what you see just by the absence of light. So if somebody, and they're actually not exaggerated pictures. This is a great example of, this is a cloud, and it just appears, at least in visible light, as nothing. And there's no coherent absorption lines because it's not like a diffuse atomic gas. It's collections of particles that are just kind of eating all light. But usually what happens is stuff that absorbs one part of the electromagnetic spectrum might be completely invisible to another part. So radio waves, for instance, might pass right through this because, the dust particles are 1/1,000,000th of a meter across, and radio waves are like a meter across, so they really just don't care. Likewise, X-rays might go through this like a warm knife through butter. Actually, that's not true, but so it's not the fact that it's not doing absorption spectrum stuff. It's just literally eating entire chunks of the spectrum. So, and visible light is the worst affected, unfortunately. Yeah. Okay. So, where did we go? That might help.
So, for example, if there's oxygen gas, you get a green glow. If there's hydrogen gas, you get a red glow.
So this guy's talking about gaseous nebula, not evil dust clouds.
It tells us what's there. It tells us what the physical conditions are, how dense it is, how hot it is, and what it's made of.
Because I should have fast-forwarded 20 more
You
seconds.
can find out a lot about the neighborhood by looking at these clues that come directly from the glowing gas.
The gases glow at thousands of degrees, heated from a mysterious source hidden deep within the nebulas. To figure out what the source is, we need to peer deep inside.
But of course, the gas and dust is in the way. So it's not so easy. It's a very mysterious part of the galaxy. It It's a place that we have to use these special tricks to look into.
And Kimberly Weaver is an astrophysicist who's got a few tricks up her sleeve.
I've got a really neat way to show you this. This is a bag that you can't see through with your eye. So normal telescope.
I don't know if we needed to be told that explicitly, but
An infrared light telescope, the infrared camera, can see with a light I can show you that you're seeing the heat. This is just like a star hidden inside a cloud of dust that infrared astronomers detect using it.
so part of the reason that she's so excited about the infrared telescope is that the technological achievement of making that camera, the CCDs, for instance, in like that recorder or your cell phone are made out of silicon. Silicon is basically sand. There's silicon in abundance. Silicon does not detect infrared light and ultraviolet light. So for infrared cameras, you have to make these really bizarre chemical things like, antimony, cadmiide, and stuff like that, and gallium arsenide doped with a little bit of mercury. And they're really expensive, and for a long time, the technology to do so was under government monopoly through by virtue of being classified. So when astronomers finally got their hands on infrared camera stuff, it's like, yes, finally. And
invisible light. You can see all of the gas here located in front of what we know are stars in the background. And we want to be able to look inside this nebula and see the stars. In infrared light, in this image, we can now pick out stars inside the nebula. And we can see dusty cocoons around the stars.
But scientists still...
okay, so one thing, just, appreciate how excited people are about infrared astronomy. But the two things about that image or this image, which is basically the same thing, one is it verifies the story about the cold cloud of gas with some chemical enrichment. But secondly, what do you notice about star formation? You look off into the cosmos and there's one little cloud of gas and then it collapses into one star. And then over there, millions of light years away, there's another cold cloud of gas and it collapses into one star. What do you actually see in this? Star formation happen alone? Many, right? Yeah, so absolutely. So there are many of them. This is in the Orion Nebula, Orion's belt. And star formation seems to occur in clusters. We just kind of talked about our own. But it happens all at once. And there's something that we missed, which I'll just point out here, is that the other piece of information that people got from finally being able to peer into star-forming clouds is that there's something kind of nuts that happened where we started with 1,000 times the mass of the sun and we ended with basically one times the mass of the sun, which is to say 99.99% of the material disappeared, which probably should disturb somebody who thinks about it a lot, and it did. One of the features that was discovered is this thing called a jet. And the jet is basically the inverse version of the aurora borealis and the aurora australis. So material is coming in at the center, and it just gets blown out by these huge magnetic fields and depleted. And these jets can be up to 1,000 AU across, so you could fit 10 copies of our solar system along this jet. They're really efficient for transporting mass. So the thing that will eventually be a star, somebody just put an aperture over it and you can't see it. These are really, really powerful, and we'll see the same structure around black holes and quasars and early galaxies, in fact. So this picture that I showed you, because I stole it from the textbook, and maybe I didn't want to explain jets, I don't really know, in fact, needs to get updated in two ways. First, that this is not a solo act. So somewhere over here, there's another collapsing cloud of dust and gas collapsing into a different protoplanetary or protostellar disk, maybe like this. And there's another one over here, and there are hundreds of these things happening at once. And secondly, there's a big structure right at the center, and it's blowing off material, which might be triggering the next star over, the next cloud over to collapse into its own star. this jet, right? So kind of updated some pictures now that we can see inside of these. And these jets are basically like, I don't know, if you could turn the motor in a vacuum cleaner around, instead of the aurora borealis where material gets shuffled in towards the poles, it's material coming in at the equator, getting blown out the ends through really strong magnetic field lines. Again, we'll see them again and again and again, exactly 3 times. Okay, so when you look at a picture like this, which is the famous pillars of creation, this is also in Orion's belt, it's a stellar nursery. There are many stars being formed all at the same time. It's like hundreds, thousands maybe for a huge star-forming cloud. And kind of what you're looking at, in a sense, because we don't see cosmic evolution over the course of human days or lifetimes or civilizations, actually, is this is how you should think about a picture like the pillars of creation. Is somebody's taking a snapshot of a shattering cold cloud of gas, and all of these pieces are shattering into their own star systems. And if you come back a billion years later, you'll have very little evidence that this stuff happened, as all of these will be individual stars, and they'll all hang out together. Most of them will, yeah. Yes.
But the stellar nursery, what would to shatter, disturb?
Yeah, so what's the agent doing the shattering? The usual suspects are a nearby supernova, which we haven't talked about yet. So some big star explosion comes and bumps everything. Maybe it just gets so cold, and we'll actually talk about this more a little bit, is that gravity starts collapsing, and then once you collapse one star, and that one star turns on its crazy powerful jet, well, what's that jet going to do to the cold cloud of gas in the next neighborhood? So it's kind of almost like a domino effect once you get it going. But I don't know, I honestly have no idea the research and numbers that support it, but the thing that I keep hearing trotted out is like nearby supernova. And my suspicion is that is true because we have a lot of evidence that our cold cloud of gas that turned into our star was absolutely triggered by a nearby supernova. Because there's all this evidence of radioactive aluminum, which is really short-lived from like 5 billion years ago. And in fact, we have like uranium on Earth, which also came from a supernova. So it happened to us, therefore it happened to everything. That's never burned anybody before in science. But something. But then once you get one going, thing starts turning on a jet, and it can totally blast into the next cloud over. So it's kind of a runaway process. Yeah. Yeah, it's coming off of, so imagine the protostar is rotating this way. And so it has all these crazy tangled magnetic fields that are very strong, and some poor particle of ionized gas comes in and gets shot out the top. Yep, very, very, yeah, very hot, very powerful. And we'll see him again. What's that? So the star, which is pretty small and rotating pretty fast at the center, has a lot of magnetic fields, and then material will come in and get shot out of them, right? So imagine that you let go of some iron filings in a magnet, they would be pushed away. This is a crazy magnet, so it'll just blow this material out somewhere. That material might smack into the cold cloud of gas next to it and start a chain of formation. Yes, but speed of light, fast. Which hopefully you can't throw things that fast, but yeah. Yeah.
Jets are like stars?
Yes. The same process that makes jets is the process behind pulsars. So very fast spinning object with some sort of magnetic field. The jets coming off of pulsars are not material, though. They're just electromagnetic radiation, but it's the exact same physics. So yeah, spinning really fast and has a magnetic field, totally. And quasars, for that matter, too, actually. Okay, so this is what you should have in the back of your mind when you see or think about star formation, is it's not, a star forms somewhere out in the cosmos, and it's this beautiful, isolated event. It's like this violent, collaborative thing. So this is really what that looks like. And you guys know enough to start your careers as stellar astrophysicists. Is I don't know, for the sake of argument, let's say that you knew somebody at one point in their life that threw a rock through a window, and just imagine, if you will, how many pieces that made. So when you throw a rock through a window, how many big pieces do you get? Shards of glass. Yeah, how many annoying little pieces of glass do you get? So many. Yeah. You guys seem like really sure of your answers. I don't know if I should be upset. So this was called the initial mass function. It's just the statistics of throwing a rock through a window. And this tells us something, and we'll keep the initial mass function, actually. It's a really important idea and a really important concept, and then we'll talk about why it seems to stop there. But really, for every big O star you get maybe 100 M stars or 50 K stars and G stars. So this is really just the statistics of broken glass, but the star-forming cloud version of it. And the important part is that you don't need to know anything complicated to know this. In fact, the more brutish your mind is, the better you understand the initial mass function. So we know how star-forming clouds start, and we know what pieces they give us. So at the end of their collapsing and turning on fusion and all that other really cool stuff, we know that we should have statistics that look like this, right? So to have a star-forming cloud that had nothing but O stars just doesn't make any sense. It won't happen. And to have a star-forming cloud that had nothing but M stars just doesn't happen. So if you looked out into the cosmos and you see a cloud of stars that all have M stars, you know something else must be going on, which is to say the O stars that should have formed are no longer around. Yeah?
Stars gather, they get more material. One, two, the ones gather slowly.
Yes, all of those things. So if you're a little bit more gravitationally rich, which is to say you started as a bigger piece, gravity is pretty anti-egalitarian, where the rich get richer. If you have a higher mass, you have more gravitational pull, so you pull more mass into you, so you have a higher mass. So you have more gravitational pull, so you pull more stuff into you, and it kind of keeps going like that. But that's kind of a microscopic, very hands-on way of thinking about it, is you just kind of think about these as the statistics of stars too. You just totally be agnostic about it and say yeah, totally, this is the distribution of shards of gas. But actually the story of how that O star got its material is started a little bit bigger, and then it accreted more material, then it got more mass, more gravity, and it kind of ran away. But you can also think about it as just this is the statistics of stars initially. This is just how the pieces break. And it doesn't really depend on, the details of that story is the important part. So, yeah. The pillars of creation, I wish I had this included somewhere, because, the two things that people keep asking are what are the colors and what are the size, and I can never remember for some reason. Is that this is certainly light years. This might be hundreds of light years across. And our maybe more microscopic computer simulations or some reasoning says that a single star-forming cloud, something like the one that made us, might start, when it got bumped, and the unit that eventually became all of the stuff involved in the disk and the jet that got blown off and the Oort cloud. You can kind of tell, because this is the size of the Oort cloud too, is maybe 500, 200,000 AU or something like that. So about a light year for us. And part of the reasoning behind that is we left behind this little trail of breadcrumbs in the Oort cloud as we collapsed. But yeah, I mean, in the sense that we call the stuff that the sun is at the center of, that was our cloud. And maybe something else happened, I don't know, but there's evidence that the material that eventually became our solar system at one point extended to about a light year away. And that evidence is the Oort cloud. But possibly bigger. I mean, I don't know. Maybe you could get 2 of them bumped together or something like that. So all sorts of things are possible. But again, no matter what weird, complicated story went on and how, may well be very interesting where jets are sword fighting with other jets and then things are getting burned off and one star-forming cloud makes a protostar that eats another one and they spin together and make a star of twice the mass, is that this is what you get. So weird details aside, this is the initial mass function. Yes. Of the things that we consider to be stars. Yeah. Just from like a... This is kind of aesthetically that it seems kind of a bummer that we'll end up with all these O star or M stars and nothing else. I completely agree with you. Is that this kind of bodes poorly for like the fireworks show of the universe if like everything ends up as just crappy little M stars. It's worse actually. So this pyramid continues. So yes, and it's not a trick of the publishing companies. Is literally like the color of each of the stars. So by virtue of their temperature. Right, so O star's hotter. Yeah, I don't know. So some things about the universe just seem like I wouldn't have designed them that way. So the fact that we're going to end up like expanding away and just have all these crummy elliptical galaxies full of M stars, I don't think a lot of people like that actually. Or run into a white hole or something like that spits more material out or something. I don't know. So, I mean, all this will happen long after we're dead, so cheer up. Okay, so to summarize, this is what we now know, is that star formation is not a solo show, so stars form in groups. Whole bunch in a cluster. Yes, some will be thrown off after they, maybe have a close encounter with another one, but at the end of the collapse of the star-forming cloud, there will be a group of stars that are still gravitationally bound to each other. We see this all over the place. They're called clusters. And the clusters, we can tell now, but for the sake of just starting the discussion, we'll assume that they formed at the same time, out of the same cold cloud. And we also know what the initial distribution should be, based on statistical grounds. So for every one O star, there are 5 Bs and 150 Ms and stuff like that. And so we have these things out there, and we know how they should have looked at the beginning of their lifetimes, the cluster lifetime. So how does this help us? Well, this helps us because this is exactly the first picture at the the high school graduation picture where everybody was born in their crappy little hometown and they take their picture when they're 18, i.e. very young, and natural causes haven't really had a chance to work. And they're going to stay there, right? So they're not going to, some, yes, may fly off to New York or whatever, but an appreciable fraction of them will stay there. Okay. And they're all basically the same distance away, so we can actually cheat a little bit and we don't have to worry about correcting for apparent brightness to absolute brightness. So, for instance, this thing called M80, which is a very big globular cluster, is about 30,000 light years away from us, but it's only 100 across. So if a star within a cluster looks brighter, it is brighter, which is really nice. So we don't have to do any complicated parallax tricks. Okay. So how does this help us? It helps us because you start seeing things, unless you saw me scroll through the slides, that you absolutely would not necessarily expect if you just knew about the HR diagram and you just knew about star formation. So pretend that you're an astronomer circa 1880 and you're very bored and you have the HD catalog, so you go into Harvard and you ransack their luminosities and you learn their arcane, soon-to-be-fixed classification scheme. And you don't make the HR diagram, you just look at a cluster and you make the cluster's own particular HR diagram, which is to say I look at this cluster and I say, oh, you're very red, so I'm going to put you in the red part. And oh, you're very blue, so I'll catalog your blueness, that's basically your temperature, and you appear to be brighter than you. So that's already a little bit weird. So the red star appears to be brighter than the blue star in this cluster. So I'll put you higher on the luminosity or brightness scale. And then you go through and you do that for all of these stars. And what you get is something that looks like this. So this is what the full HR diagram should look like. But now you know that there are some statistics hidden inside of it, right? So it should have 1 of those and 5 of those and 50 of those and 120, 150 of those. So this is a little bit cartoony, where these things are just a representative star. This is what you see when you look at an actual cluster. And the units are the same, so there's no funny business there. This is the sun just for reference. So I see the tail of what seems to be the HR diagram, but then there's this. What is that? And then I see this. The HR diagram is basically gone from the sun upwards, and then it has this weird breakneck, comes up and makes this, I don't know, this kind of seahorse-looking thing. Is this at all what you expected to see based on your knowledge of the HR diagram? What could possibly be happening? Maybe we can start with a really easy question. So I just looked at a big cluster that's pretty high above, it's not tremendously important. This would be a globular cluster pretty high out of the galactic plane, lots of stars. But which are the ones you can't see? This is why I'm confused. So the ones I can't see are O stars. Yeah. So if you're absolutely right that if I was missing M stars, and I kind of am, so you see a lot of them here and then it kind of trails off, there are absolutely stars there, you just can't see them. So there's some selection bias. But the selection bias is not the one that I would expect, where I can't see the O stars. So where are my O stars? They did, yeah. How old is this cluster, at least? Yeah, because they're gone, right? And now we have some information about how they're dying, too, because now we can probably imagine that, these are stars that are leaving the HR diagram's main sequence. So maybe we are starting to learn about how they're, passing away. In fact, I don't see any B stars either, so how old is this cluster? Must be 100,000 years old, and then sun's about 10 billion. Blue stars, like A stars, are about a billion years old, so that would be a billion years old. How old is this cluster about? The stars that are leaving the HR diagram right now are about at like the 1.5 billion, 2 billion mark. Apparently this is a 2 billion year old cluster, because all the stars that have a lifetime of less than 2 billion years are gone. And we have some weird residue here. I don't know what that's about. And then we have some funny business up there. I don't know what that's about. Something, right? So the thing that you can tell me unambiguously is that they seem to be getting, let's just imagine that this thing is kind of peeling off that way, is that this star is kind of going that way. It seems to be getting a little bit cooler and a little bit brighter, which is kind of odd. Cooler and brighter. So these are like their death shroud remnant hot gas things. Could well be. That's a correct component of what you're seeing. It's not the entire story, though. Sorry, it was a question, comment, none of the above. What's causing this? Lots of things. So this is the story of low-mass star death. And we will take an entire day to talk about it because it's pretty interesting, and because this is the fate of our sun. So our sun's going to do this in about 4 billion years. So each one of those parts that you see, the upswing and then the pause and then the wild jerk back to the other side, the so-called horizontal branch, and then weirdly reporting down here, all this stuff, that's all in our sun's future. So we'll talk about that in detail with the low-mass star stuff. Just sorry to keep stringing you guys along, but our job right now, and we'll finish up pretty quickly because we basically have the answer, is how old are stars, so the ages of particular stars. So what can I tell about the ages of every single star within this cluster? So they're all formed at the same time. So by virtue of this thing being the last one on the HR diagram, and you imagine the next star to die, whatever that means, or go off that way, has a lifetime of about 2 billion years. All of these stars are 2 billion years old. Okay. So this is what's called a cluster HR diagram. And the analogy to the high school yearbook picture is we know what should the statistics of stars at the beginning of their lifetimes. This isn't really true, but imagine that, brunettes had a third of the life expectancy of blonde people or something. I don't know if they need more advantages in life, but whatever. That I would come back after some amount of time, and then all of the brunettes would be gone, and I would just have, these awful people with light-colored hair, right? So it's really initial mass function plus the ravages of time, which are easier to understand for stars than people, leaves us with this. Likewise, the initial mass function, as evidenced by the diagonal part of the HR diagram, so all the main sequence stars, except there are many more of these than those, plus the ravages of time give you this. So we get to learn two things. One is the age, and secondly, by looking at all those weird kinks and curves and extra parts, we'll figure out how stars actually leave the HR diagram. Okay. So the important part, first bit at least, is this. So the last star on the main sequence is called the main sequence turnoff point, and that's really, that's the next star to burn through its the hydrogen in its core and stop fusing. So, yeah, they're all ticked out. I don't know if you can see, and even in the middle of the classroom, but they're all like little X's. So this would be one star. Sorry, star if you want to get untechnical about it. This is a bright thing that I see. So is that. And each one of these, there's so many symbols that they overlap. Yeah, so the sun is 10 billion, has a 10 billion year lifetime, and there are stars that are a little bit hotter than the sun that are about to burn out. So what I did is I basically looked at where these things are about to leave the main sequence, and that's like an early G or late F. And then I went up here, said early G, late F, somewhere around here. So 2-ish, somewhere in between 1 and 10. Not necessarily. Some of them are, which is why I'm kind of equivocating. But the things that are truly stars are not necessarily getting colder. In fact, it turns out that some of these are actually moving that way, which means they're getting hotter. So these, if you really take... So we don't know what time does yet, but it turns out that you really actually do follow this trajectory up and back. So in fact, you get a little bit colder and more luminous, and then you get hotter and less luminous. But a star sitting on the main sequence just sits there burning through its main sequence fuel. In fact, the sun's actually getting a little bit hotter as it lives through its life. Okay. So don't worry too much about the units. Just say they're an analog of temperature increasing this way, hotter, colder, and brighter, less bright. But they've been mapped onto absolute brightness. So here are a whole bunch of clusters. Which is the oldest, which is the youngest, which is the reddest, and which is the bluest? So oldest one would be what? M67. Why? Yeah, its main sequence turnoff point is way down there, right? Which one's the youngest cluster? NGC 2362. Which one would be the reddest looking cluster overall? So I took all the light and I blurred it. M41 is that plus that. So you could make a case for M41. There's some red stars in M41. Yeah. Another possibility for the reddest might be M67, because it's totally depleted of blue stars. What about the bluest? Also, probably NGC 2362, or Ancient Persei was the one I found a really good picture of, so I did that. And lastly, I like this mnemonic because it kind of puts the relative times on it, is that somebody came up with the analogy of star cluster as a candle marked out like this. So you have the O stars at the tippy top, and then the A stars, F stars, G stars, and then M stars. Don't worry about it. The candle goes like 10 meters this way. And you light the candle when you form the star cluster, and then it just burns through. And if it's burned through all its B stars, you know it's a certain age. If it's burned through its Bs and As, you know it's a certain age. And if it's burned all the way down to the Gs, for instance, you know that it's like 8 billion or longer years old. And then it just keeps burning through the higher spectral types. Yeah. Over the course of their main sequence lifetime, yeah. So when a star is sitting on the main sequence, it basically has the same spectral type and temperature. Yeah. But remember, this is it's a logarithmic graph. So from here to here is a factor of 10. So if the sun increases its brightness by 20%, which it actually has, it's moved from here to here. So stars do wobble a bit over the course of their lifetimes, but like from there to there. So they're not like wildly, getting hotter and right. Because really, it's like your mass determines your temperature. Okay, so the candle burning analogy I kind of like, and these are they. So this is H and Chi Persei. Really, it's even hard to see the light from the non-O and B stars. So it's really just dominated by the really young, bright stars. And again, the M stars are 1/10 of 1/1000th of the amount of luminosity. M11 is somewhere in the middle. I actually kind of see a mix of white stars and some red stars. A lot of the red stars will be these things called super red giants, which we'll talk about later. And then M67, so that's a foreground star. Don't worry about that. Really red. All that's left are the Ks and the Ms. So it's like gone. Okay. It's a great question. Absolutely not. But they're all visible light. They're not taken with the same telescope. So even these, the images are reconstructed in some fashion, but you kind of hope that they don't do anything too wild to you. So probably not the same telescope, but they are pretty good representation of what your eyes would see. If you were to zoom, go all the way out and get a good look at the H and Chi Persei cluster. Now it's in kind of boring time, actually. So and this is the goal of next week, is there's this really strong divide in some stars like throw a tantrum at the end of their lives and some stars don't, and the divide's about there. So it's really wild stuff for the really young clusters. Like H and Chi Persei, you come back and there will be like supernovas and black holes forming and all sorts of wild crap, and then it gets to here, and then for the middle age to older clusters that have just low mass stars, about 2 solar masses and less left, it's pretty boring. So they'll make red giants and pretty planetary nebulas. Occasionally you might get another type of supernova, which is pretty exotic, a type 1a supernova, but I don't know. If I wanted to sit there and look at one of these things for something like crazy, it would be that because it's really young, or that, weirdly, because it's really old, and it might have things like neutron stars, which have collected planets or something like that. So nobody thought that would happen, and it did. But yeah, so this is, I think, at the start of boring time, honestly. So all the supernovas have gone off. But that's next week, the different ways that stars die. Good. Other questions? Okay. So this is it, and we have a pretty good answer. It's not a complete answer, but if a star lives in a cluster, then we can determine its age. If a star is hanging out all by itself, no cluster, solo act, then good luck to you. There are ways of trying to do it, something called stellar seismology and things like that. But it's really, if you're in a cluster, you can figure it out. So one of the great triumphs of this is that no cluster has ever been found that is older than 13 or 12.5 billion years. So it's actually like one of the totally independent checks on the Big Bang Theory that nary a cluster has ever been found that's like beyond 12.5 billion. So oldest you can possibly get. If we found one that was 15 billion years old, everybody would just stop and have to reappraise a lot of things, and there would be pandemonium in the world of science. Okay. So this is where we're going to go next after this, is we found that there are these 3 new clumps of things, and they behave in a funny way. So they're the so-called white dwarfs. They're overall pretty non-luminous. Remember, this is logarithmic scale, so 1/10,000th of the sun's luminosity, but some of them are really hot, like 40,000 degrees, geez. So they're small, they're hot, white dwarfs. There's a giant branch and the supergiant branch, and kind of the dividing line in between them is the high and low mass star divide. Okay, so now if you're interested in doing that and have no questions about midterm stuff, but at some point we'll start exercise 7, which is basically finding the ages of stars and following stuff through cluster diagrams. And once you put in the effort to do that, then the payoff is really just get to talk about sci-fi stuff. So these are stellar remnants, X-ray, visible of planetary nebulas. So this is the kind of stuff that our sun will eventually leave behind. And I couldn't get a real picture of a black hole because they don't exist. So this is an artistic representation. The high mass stars leave behind things like this. So this went off in 10,006 AD, as witnessed by Chinese and recorded by Chinese astronomers. It's already like 60 light years across. So this is insane. And sitting inside of it is a pulsar. So that's where we're going next. So any questions about that stuff? You absolutely can't wait for 7 days to ask.